ROM and RAM mostly they're built using MOSFETs and BJTs, but there's a difference between the two. MOS has higher packing densities. They occupy less integrated space compared to BJTs, and they also consume less power. But also BJTs have their advantages. They have faster access time, and this and this disadvantage. Sorry, this and disadvantage: lower packaging density. Due to this, diode-based ROMs have become obsolete. So most ROMs are made using only MOSFETs. So I'm only just going to dive in. Sitaingia ndani kabisa. Sitapitia kila kitu. So nitapitia tu vitu juu such that you get the gist of everything and we can pitia the questions. When we pitia the questions, you guys will be okay. Mkifanya in a ROM, data is stored in rows and columns. For example, a simple 8x4 ROM uses data being stored in the ROM, and oh, I'm breaking. Well, my internet is bad. There's nothing hapa. Okay, mnanisikia vizuri saizi? Please somebody say yes kama mnanisikia.
Yes.
Yes.
Nilibreak wapi? Situna?
Near the where you started row and column decoding, just around there.
Oh, okay. So, let me go. Row and column decoding. So let's assume, let's take an example. A simple 8x4 ROM uses a 3 to 8 line decoder. So data being stored in the ROM, and the 8 represents the address where each bit is stored. So 4-bit data is stored in each of the 8 memory locations, and it uses a decoder to select those address lines. So sorry, there's the input and there's the output. So the input usually is n, and the output usually is 2 power n. So mshike hiyo. So like here, it's stored in 8 memory locations. A decoder selects the address, the row in which the data is stored. So tukiendelea, we take 32K is the memory locations. Would require 15 to 32 768 decoder to input data, to read data from, to input data, sorry, into the memory locations of the ROM. So E32768 ni kumultiply to by 1024. So normally tunge construct such a decoder, but it's not economically viable, so itakuwa tangle and it will be difficult to fabricate. So mostly what we do, we take the memory capacity of the entire ROM, then we get the square such that it has a geometrical structure like a square or a normal rectangle. So that is how we construct it. Mtaiona mbele. This is just an explanation of it. Alafu we use multiplexers also in the decoding, mtaona. So let's take an example. Here the decoder is used to select rows in a memory cell matrix, and a multiplexer is used to select columns in some of the ROM diagrams. So an example, a simple 256 by 1 ROM. This would have 256 rows and a 1 column to give a total memory cell count of 256. So instead of having a 256 by 1 layout, we take the square root of 256 so that we get a 16 by 16 matrix, so that there will be 16 rows and the 16 columns. The 16 rows would be selected by a 4 by 16 decoder because the outputs will be 16 and the 4, and the columns will be selected by a multiplexer. Output data, the output data is always equal to the number of multiplexers you use. So I think so. Yeah. Tutaona tu mbele. So in addition, the output buffer stage can be used to chip select lines, CS1 and CS2.
Nigel?
Okay.
Nigel,
Yeah.
before you go too far, can you please go hapo mali umeandika the
Yeah.
16? Can you explain more hapo kwa however the cells can be arranged?
Yeah.
Hapo kwa the 16 rows can be selected by 4 by 16 decoder and the 16 columns. That part. Can you please explain more? Sijaelewa.
Oh, okay, sawa. So tumesema nini yetu ni 256 by 1 ROM. So kupata memory cell capacity, the memory cell matrix tuna multiply 256 by 1. Kwa kupata memory cell capacity ya hii itakuwa 8 by 4, hii itakuwa 32k by 8, same. So in order for our ROM to have a geometrical structure that is economically viable, inaweza undwa without creating wastage, we try to make it like a square or a rectangle, but hii 256 by 1 itakuwa na 256 rows like this, 256 rows, alafu just 1 column. So rows zitakuwa mingi, alafu column itakuwa moja. So instead hiyo kitu itakaa ndefu, like itakuwa una get the idea. But now in order to make it like this instead of it being this, matrix yetu itakuwa by 16. Tutafanya example alafu utaelewa. The 16 rows itakuwa selected by a 4 by 16 decoder because a decoder select rows alafu the multiplexer selects columns. So the decoder itakuwa 4 by 16 deck. So in addition, output buffer stage will have chip select lines, CS1 and CS2. You'll see how we implement that. This is just a review of the multiplexer. Unaweza pitia kitabu ya Professor Mwangi, but it's just like a page long. Itachukua tu like 10 minutes to understand it. So applications of the ROM, it's used in implementation of logic functions. PL, PLA, like at easy, they are used in implementation of logic functions. It's also used in code conversions and lookup tables. So moving on to EEPROM. MASCROM na PROM ni more or less the same thing. So if that's what I said, the difference between PROM na MASCROM, it's just that fabric bits data on your house. In your house. Reprogrammable ROMs are the EEPROM and the double EEPROM, where the major difference is the erasure method. This uses electrical signals. This one uses ultraviolet rays. EEPROM has a wider usage than the double EEPROM. EEPROM has a wider usage than EEPROM, hence warrants further discussion. So we're supposed to study this, but this one is not used mostly, so we don't study it. So the operations of an EEPROM, this is how it looks like. An N-type, it uses MOSFETs. So this an N-type MOS and a P-type MOS. There's a floating gate over here, then P substrate, the source, the gate, the floating gate, the drain, this is the aluminum plate tips, and the silicon dioxide, semiconductor material up and down. So programming of EEPROM. So a high voltage is applied to the floating gate upper Ju. It causes the voltage now causes electrons to be injected into the substrate, either the P substrate or the N substrate layer, through the dioxide into the floating gate. So in dioxide ndio itakuwa the barrier katikati. So electrons zitakuwa zinatoka hapa zinaingia huko, ama zinatoka huku zinaingia huku, depending on whether you're writing data or you're erasing data. Same to this one. So for that to be achieved, for programming to be achieved, voltage must be large enough to excite the electrons such that they jump from the substrate past the silicon dioxide barrier. The voltage is usually 20 to 30 volts. Vitabu zingine zinasemanga 35. When the programming voltage is removed, the charge is trapped in the floating gate. Remember, charge iliruka kutoka huku ikaingia huku, but now when the voltage is removed, itakuwa trapped hapa ndani, hapa itashindwa kurudi. And it is insulated from the entire device by the silicon dioxide layer. So the stored charge in the floating gate, it alters the threshold voltage of the MOSFETs. In such a cell, a channel can't form between the drain and the source, between the source and the drain. A channel and the source voltage and the drain source voltage, such as VDS, and get voltages. Right. The threshold voltage of the MOSFET is altered in such a cell. A channel can't form between the drain and the source when suitable drain source voltage and VG get voltages are applied. Oh, okay. So for a charged cell, current can't flow because the drain and the source, there is no connection there. So a 0 bit is stored. So technically, when an EEPROM comes, ukinunua, it just has one stored in it. You have to apply a suitable voltage at the gate such that the electrons are excited from the N-oxide layer. Last current can't flow, so 0 bit itakuwa stored. But when you buy it, it's just one stored in it. So in order to erase the data, the EEPROM is exposed to high intensity UV through quartz window on the surface of the chip for about 20 to 30 minutes. So the ultraviolet rays, itaipatia energy. So the trapped electrons inside the enough energy kurudi the barrier and then go back to where they were. Hence, this, and it can conduct and it will have a 1. So basically that's it. KPTI is simple enough. So on to examples. Examples are ROM sasa. Example 1, give the structural layout of a 16K by 4 ROM. Okay, this, as we said, is the data that is stored in each memory cell location of the ROM. So 16K and the memory cell locations, the addresses. This is the 4-bit data yenye iko stored in it. So kupata kumbuka tulikuwa tunatumia decoder kuselect rows, alafu itakuwa n itakuwa times 1024 inatupatia 1634. So it's a 1634 by 4 ROM. So in order to get the number of input lines, the number of output lines, of the decoder, these are the number of output lines that are supposed to talk out from the decoder. So to get the input lines, 2 power n is equals to this, we get the value of n. So 2 power 14 itatupatia hii. So the number of input lines from the decoder itakuwa 14. And a decoder normally is inside a ROM chip. So let's assume these are 16K by 4 ROM. So the decoder iko hapo ndani. So the number of input lines itakuwa 14. Alafu the number of outputs zinafaa zikuwe, tutaignore hii yenye niliandika hizi mwanzo. Data out sasa inafaa ikuwe 4. This is a 16K by 4 ROM. But now we're supposed to start construction by using a decoder now. So we got the number of input lines. So the number of input lines is 14. Mshike kwanza. We'll use it later on. So to get the memory cell capacity, mesh sasa, it's here. Instead of constructing a 16384 by 4, so itakuwa na 16384 rows and 4 columns, it would be uneconomical to construct such a thing. So we get the square root of this in order to get a geometrical structure that looks okay. So the square root of it itakuwa 256. So this gives us 256 by 256 memory cell, such that there's a 256. So this side is 256. Also, the columns is 256. So there's supposed to be lines like this. This is the memory cell matrix now. Alafu, remember we said that decoder is used to select the rows now. So if the output of a decoder is 256, what's the input of the decoder? It's 2 power n is equal to 256 upper. So the input lines itakuwa 8. So hivyo ndo nilifanya hapa. Decoder. So tukiendelea, since we have 14 input lines that we got from here, the total number of input lines in the cell, we can subtract 8 lines from the decoder, so that we remain with six lines zingine. The other 6 lines, remember we said that a multiplexer is used to select a column and a decoder is used to select the rows. So the multiplexer, the inputs, remember a multiplexer is a data selector, it selects data. So the select lines will be these 6 input lines zenye zilikuwa zimebaki, na kupata the number of input lines from a multiplexer itakuwa 2 power 6, itatupatia 64, such that multiplexer yetu itakuwa a 64 by 1 multiplexer. So hii side itakuwa select lines zitakuwa 6, alafu hii itakuwa output because multiplexer inakuwa tuna one output. So sasa the input itakuwa 2 power 6 which is 64. So and remember tulipata memory cell matrix yetu kwa 256 by 256. So if one multiplexer ni 64 by 1, so tunachukua 256 divided by 64 to get the number of divisions that we're supposed to put inside our memory cell matrix. So we get 256 divided by 64 inatupatia 4 divisions. That's why nili divide hapa mara 4, so that we can multiply 64 by 4 itakuwa 256. So the output goes to each multiplexer, and the select lines of the multiplexer, it's common to every multiplexer hapa. So inatupatia 6 yenye tulipata hapa juu. Each multiplexer now, remember there are 4 multiplexers. So niyo hii itakuja kwa D3, D2, D1 na D0. Alafu there is a chip select kwa nodes hapa. In addition, an output buffer stage can be used with chip select lines CS1 and CS2. So that's why we've included it hapa to each our buffer. Then get our data out to be this. It will be 4-bit. So remember nikisema the number of multiplexers shows up. Oh, okay. Okay. Oi, kumekuwa na maswali. Could you come again at the part umesema multiplexer does so and so, please?
Start from Kamara's.
Where? When the capacity isn't a perfect square. What? Upper. When the capacity isn't a perfect square. That's a question, Amo.
No, from Michael's question.
Oh, from Michael's question. Could you come again at the part umesema multiplexer does so and so, please? Okay. This is our multiplexer. So it has select lines like S0, S1, and it's used to output data. And the data and the input lines of our multiplexer. Wait, I have to confirm this how. Or the input are usually the power of 2 power, okay, like here 2 power 6 is equals to 64. So the number of select lines, 2 power, the number of select lines gives us the input lines. Like hapa, tukona only 2 select lines, so 2 power 2 inatupatia the number of input lines za mux yetu. So ingekuwa like nikiongeza hapa itakuwa S2 itakuwa 2 power 3 inatupatia 8. So itakuwa the tunaongeza zingine 1 2 3 4 5 6 7 8 like that. Alafu inatupatia one output. I can't remember what goes on inside here, but basically that's just the entire gist of it that you need in this question. Wacha wakina Fiona wakipresent ndaipitia, alafu wakimaliza kupresent ndakuexplainia vizuri on how it works. Just a multiplexer. Alafu, how do you choose how many multiplexes you need? Okay. Like here, we're supposed to design a ROM that as to give a structural layout of a 16K by 4 ROM. Alafu, initially, we started by finding the number of pins, input pins that give data into the ROM. So we were supposed to multiply this 16K by 1024, ndo tunapata 16384. So to get the number of input lines, ni 2 power n. So n itatupatia 14 input lines. So 14 input lines, just put a pin on that, tutarudi hapo. We get the memory cell capacity now. It's 16384 by 4 from here, which gives us 65,536. So 65,536 is the memory cell capacity. We find the square root of it, get 256 by 256. So 256 is our memory cell matrix. So it needs 256 rows and 256 columns. And input, it's used in inputting data into the rows. Yeah. A decoder is used to the rows. Yeah, that's so sisi tuko na the number of rows. The number of rows is 256. So to get the input lines of the decoder is 2 power n is equals to 256. So we get 8. Now, Elizabeth, we've already gotten the input lines into the decoder. So we need, in total, we had 14 pins that were giving data into the ROM. So sai, tuko na 8 pins zenye zitaingia kwa decoder. So the rest of the pins zinafaa ziingie wapi? The rest of the pins, 14 minus 8 is 6 pins. 6 pins zinafaa zikuwa data selector ya multiplexes. Alafu from swali ya Mike, to get the input of each multiplexes, we get 2 power the number of select lines, which is 64. But now remember, input line zake ni 64. Input line zake ni 64. So, how many multiplexes will we need to input data from 256 columns? So we just take the number of columns divided by the output. Sorry, divided by the input of that multiplexer that we found, such that it equals 256 divided by 64. Alafu tutapata 4, such that gives us the 4 multiplexes. Okay, that's a long method, lakini itakusaidia ukiendelea kuifanya, but just generally, if you see the number of data,
yeah,
the number of, yeah,
you know, that was
the number of bits. Okay, yeah, okay. If you just see the number of bits, that's the number of multiplexes. Like, that's the short form method, but I think we can calculate understand the long method itakuwa like it'll make a bit. Oh, Glenn amekam. So does that mean that the 6 remaining lines from the original 14 are select lines for the MOOCs? Yes, Glenn. Oh, ameshajibiwa. So there's no other questions here. Okay. So we got our data out to be D0, D1, D2, and D3. So in order to confirm what we've just drawn, like, so to read the data content of this address, we take the most significant bit to be this. The most significant bit will always be the one of the decoder, and the least significant bit itakuwa the select lines of the multiplexer, F5 to A0. So this one, 1001, 0001, itakuwa decimal 145. The most significant bit, alafu the least significant bit itakuwa decimal 58. So raw number yetu essentially from the decoder itakuwa 145, alafu column number yetu itakuwa 58. So data yetu itakuwa stored kwa hiyo location, alafu kama unataka kusoma hiyo data utaipata kwa hiyo location. Let me look for a similar question ndo nijaribu kucement whatever tu yenye nimesema. Okay. Question. I don't think I have a similar question to that. Celeste?
Yes.
Kwa maswali zenye ulituma, kuna yenye ni similar to that?
To the one we've just done?
Yeah.
Yes. Yeah.
Okay,
Yeah.
okay. Yeah. Wacha nitafute. Siko sure. So just a minute. Just a minute. 45 minutes has passed. Ama niendelee tu na maswali zenye niko nazo, then if time remains, tutapitia swali. Let me continue just the swalis I have, then ikisha load na kaa kuna time after kina Fiona wamepresent tutazirudia. So question 2. Design a combinational circuit using a ROM. The circuit accepts a 3-bit number and outputs a binary number to the square of the input number. This is a similar question to what akina Fiona did, so I'm just repeating it. Na niliona swali kai kwa I think papers mbili. So in designing this combinational logic circuit, it accepts a 3-bit number and outputs a binary number equal to the square of the input. So input tuseme inafaa equal 3, output itakuwa the square of that. So input yetu ni 3-bit, so I drew this table. So I listed all the I don't know what they're called, the min terms till 7 ya mwisho. So the maximum square of this data itakuwa 7 by 7 because this is just the decimal, the binary of the decimal. So maximum square itakuwa 7 by 7, which is 49. So for now, just ignore this other part. Nitaendelea explain as I go along. So just focus on yenye nimesema. So the maximum square is 7 by 7. So in order to get its binary bit, yenye itatusaidia kuchora this part of the table, we take 2 power 5. We try to get what? We try to get a value that is close to that 49 while squaring 2. So like tuseme maximum square yetu ingekuwa tuseme 5 by 5 ingekuwa 25. Tungekuwa tunafanya 2 by 4. 2 by 4 itatupatia ngapi? 2 by 4 is 16. So this will give us 16. So this gives us 0 to 15. Alafu 2 power 5 gives us 32. So 2 power 5, sorry, 2 power 5 gives us 32. So this 25 is between 16 and 32. So we go for the higher one yenye itatusaidia kuchora hii part. So hapa maximum square yetu ilikuwa 7 by 7. So I did 2 power 5 which is 32 gives 0 to 31. Haijafikia square yetu. So I did 2 power 6, it's 64. So value yetu iko in between hapo. I took the higher value. The value is in between. So I took 6 bits. So our square is supposed to be a 6-bit value. So that's why I put B0, B1, B2, B3, B4, and B5. So those are 6 of them. So tunakuja ku square now. So the first bit, we multiply each bit by 2 as we go on. It will help us to fill this table like this. The first one itakuwa 2 power 0 such that itakuwa 1. Alafu we multiply everything by 2. So 1 by 2 is 2, 2 by 2 is 4, 4 by 2 is 8, 8 by 2 is 16, 16 by 2 is 32. So hii itatusaidia kupata the square of this value of ours. So like 000, it's binary bit. It's a binary bit of 0. So 0 squared is just 0. So nika input 0 hapa. So 1 squared is just 1. So penye 1 iko nika a value of 1. So everything else was 0. So for 2, it's 0, 1, 0. 2 squared is 4. We have our value 4 here. So I put 1 core 4. Everything else is 0. 3 squared, same thing, 9. But now we don't have 9, is 8 and 1. Hapa. The rest is 0. 4 is 16. Square yake is 16. So I put 1 in 16. The rest, it becomes 0, 5. It's 25. So 16 plus 8, which gives us 24, plus 1, which gives us 25. So the rest are zeros. Alafu 6 gives us 36. We have 32 upper, and we have 4, gives us 36. So the rest becomes zeros. 7 is 49. 49, we don't have 49, so 32 plus 16 plus 1. Alafu, from this question, you're supposed to minimize the number of terms you're using, such that ukiona terms zenye ziko similar, you just group them, like this one. B1 is a 0, so it's instead of inputting it into our ROM, it will be a waste, so we just put B1 to be 0, mtaiona later. Alafu B0, we can see there is a pattern, 0, 1, 0, 1, 0, 1. Also C is 0, 1, 0, 1, 0, 1. So we equate this one to C. So the line yenye B0 itatumia tu line ya C. So tukikuja kuichora, wamesema combination logic circuit accepts a 3-bit number and outputs a binary number. So kwa ROM, kumbuka tulisema data inaingianga through a decoder. So our input data is supposed to be 3 bits. So ABC, output yetu itakuwa 8. So I drew easy output lines, 8 of them. So from the 8 output lines I drew, also we say that B0 is equals to C. So I just nilitolea huku. Okay, later B0 is just C. B1, it's 0. So I just put B1 to be 0. So B1 will always be 0 regardless. Alafu B2, B3, B4, na B5 niliziweka kwa OR gates hapa. And I didn't fill them out. So I wanted to fill it out with you guys. So for 0, it will just be 0 for the first line. For 1, B0 will have a 1. And B0 is C. So when it is a 1, we just don't need to fill it up. For 2, it's 0, 0. B3 is 0. B2 has a 1. So it's for 2. Has a 1 other. Alafu for 3, B3 has a 1 and B0 has a 1, but B0 is BC. So B3 has a 1. For 4, B4 has a 1. For 5, B4 and B3 and B0 have a 1, but B0 is just C. So we fill for B3 and B4. So B3 and B4. Alafu for 6, it's B5 and B2. The rest are zeros. So it's B5 and B2. Alafu for 7, it's B5 is 1, B4 is 1. So B5 is 1. Sorry, this is B5 and B4 is 1. The rest are zeros. But B0 is a 1 and B0 is C. So this is what we're supposed to come up with later. Like the answer, sorry. So this is just our answer. There's a question I saw about a 4-bit number now. So itakuwa to the same process, but sasa tutaongeza D. Alafu for 4 itakuwa how many of them? Itakuwa 15. Itakuwa 15 minterms, so 15 by 15 itakuwa square yake itakuwa 225. So tunaendelea to the same process. It will just be longer, but it's the same process. Kuna mtu akona swali? Okay. What did you give to get the maximum square? Okay. We're supposed to, so 3 itakuwa 7 times 7. So kiwa 4-bit number itakuwa ABCD, minterms zake zitakuwa mpaka 15. So kupata maximum square yake itakuwa 15 by 15. Ama, is that what you're asking? Ama I should go further? Okay. So, tukiendelea 956. Okay, let me just hit here these two. Nikidogo. A ROM chip of 4096 by 8 bits has 2 chips select inputs and operates from a 5-volt supply. How many pins are needed for the integrated circuit package? Draw terminals in the ROM. 4096 by 8 bits. This is the data output, and this is the memory locations where the data where the 8-bit data is stored in each of the 496 memory locations. So kupata inputs of the ROM, tunapata 2 power n of the memory locations, such that ni 12. So kwa swali kai ametuuliza tupate the pins za the integrated circuit yote, including the VDD, the output lines and everything. So ROM yetu itakuwa inafanana hivi, 4096 by 8 ROM. So the input pins itakuwa 12 from here. The output pins ni 8 from the 8-bit data hapo. Alafu wamesema 5 volts power supply, VDD yetu ndio hapo. We always should include a ground hapa. Alafu and wamesema it has 2 chip select inputs. So CS1 and CS2. So in how many pins are needed for this integrated circuit package, we just hesabu all these pins. So 12 plus 8, 20, 21, 22, 23, 24. So 24 pins needed. Yeah. This is this one is similar to what I did here, upper, but there is just a simple twist because they tell you to, okay, let me just take you guys through the question. Sitaifanya, lakini mnaweza ifanya on your own. So using a 64 by 8 ROM chip with an enablable input, construct a 512 by 8 ROM using a decoder. How many ROM chips will you need? So one chip is 64 by 8. 8-bit data, 64 memory locations. We're supposed to construct a 512 by 8 ROM. So this one is the bigger one. So how many of these will be used to make these? So we take 512 divided by 64 to get the number of chips. So after we've gotten the number of chips, we can use it to create our memory cell, not our memory cell. We can use it to, after getting the number of chips, we all include them hapa kwa structure yetu, alafu the number of chips zitakuwa selected using a decoder through their chip enable. So the chip enable, so kila ROM chip itakuwa na enable, alafu decoder yetu itakuwa inatusaidia kuselect the number of ROM chips, alafu itakuwa na a common line, because decoder yetu itakuwa na 3 inputs, kutakuwa na common line yenye itakuwa na 6 inputs. Alafu utapitia tu hii nini with the explanation. Kama uko na swali unaweza niuliza, alafu kuna one more question, but I think sitaki kubatin kwa time ya watu, nisha kula time ya watu. So kama kuna mtu ako na swali auliza, I can present if there is more time later on, but I think this is enough. Okay. Alvin was supposed to take you guys through RAM na DRAM, but naona nimekula time sana. So Fiona na Gisheru sijui, I think you guys will go, then I don't know how we're supposed to go about it. Anyone?
I think let Fiona and Gisheru go first.
Okay.
Hi. Okay. So let me present my screen. Just a minute. Let me know if it's showing someone. Hello?
Yeah, yes, please.
We can see it.
Okay, thanks. Someone please to have their mic on so that to tell me if there's a question, because presentation mode, I have to go back. So with logic families, we have ECL, TTL, we have NMOS, PMOS, CMOS, and pretty much that's it. So we've tried as much as possible to do a question in each. So I'll just dive in. So So, okay. So, Ombalo did one of the TTL in the previous video. I think that's the first DE discussion we had. He explained on TTL and how it works. So I don't want to stay there and explain because the recording is there and he sent his work and the questions which he attempted on TTL. So I'm going to do the example 3.1. There are the parameters of the transistors in the open collector. For this, so this is a circuit. It's a 2-input open collector gate. It's a standard TTL, but now without T4 and the diode. So, I determine a suitable value of a passive pull-up resistor that ensures a power dissipation of no more than 15 milliwatts. So what is supposed to happen?
The screen is frozen. Maybe it's just me.
Yes?
Like, I think it's, or maybe it's just me.
No, it's also frozen for me.
Just Google Meet tab.
Now we're on Google Meet.
Yeah.
Okay.
Like, are you presenting a document at the moment?
Yes.
Okay, we can't see it. We're only seeing you're presenting to everyone on Google Meet.
Okay. Okay, I've seen what I did wrong. I presented my window instead of a screen. Okay. So someone will let me know once it starts showing.
It's now presenting.
Okay, so the question is, find a suitable passive pull-up resistor RC3 that ensures a power dissipation of no more than 50 milliwatts. So we're supposed to look for an RC that can fit, that will ensure that there's power dissipation there. So the first thing, so we are told HFE is 35, the dB SAT is 0.75, and we see SAT is 0.2. These are things that we know. So that's RC3, we need to find RC3. But what is power dissipation? Power dissipation is the average of power dissipation for logic, low output and high output. So when we have a high output with TTL, we usually say that when we have a high, when we have a high output. Wait, what is this I wrote here? Wait. Yes, when we have a high output, D3, T2, and T3 are in cutoff. If anyone has a question, please ask. D3, T2, and T3 are in cutoff when we have a high output. So PDH, because T2 is in cutoff and T3 is in cutoff, we cannot take into account current IC2. So we can't take into account current IC2, and we can't take into account current we can't take into account current IC2. So power dissipation is VCC times ICCH, and our ICCH will now be equal to IB1.
Where is the D3 coming from?
Sorry?
Where is the D3 coming from?
D3. Oh, D3. When I was analyzing it, the D3 is when you see how when we have the multimeter for the standard TTL, and we usually have sorry, my laptop is misbehaving. Sorry, wait. When we have, you see, there's this T1 here. Can you see this T1? Mm-hmm. So when we usually have that arrangement for the diodes, we usually say
the multimeter.
Sorry?
For the multimeter.
Yeah, it's from the multimeter. That's the D3 I'm talking about.
Sawa, thanks.
Yes, that's the D3 I'm talking about. So IB1 will only consider IB1 through RB1 as that's where current will only go. It won't go to, because T2 is off. So VCC times ICCH. So IB1, we know IB1 is equal to the current through the RB1 is VCC minus VB1 over RB1. Sindio. But what is VB1? VB1, when we have a high output, it means VB1 will be equal to 0.2 volts plus 0.7 volts. That will give you 0.9 volts. Okay, is there a question there? Okay, so IB1 will be 5 divided by 5 minus 0.9. You divide by 4K, you get 1.025 milliamperes. Sawa. Okay, so PDH will now be equal to this IB1 times the VCC, and our VCC is 5 volts. So it will be 5 volts. Yes.
Hapo kwa VB1, where does 0.2 come from?
Kwa? Oh, so
0.2.
Okay, the 0.2 volts, we are assuming because it's an input. It's an input low, so we are assuming our low is logic low is 0.2 volts. So it will be 0.2 volts plus the voltage across the diode, which will be equal to 0.9 volts. That's the assumption that we make now.
Okay, yes, thank you.
Low input is 0.2 volts. So,
yeah, thank you.
Okay. So, PDH will be equal to 5 volts times the current 1.025 milliamperes. You get 5.125 milliwatts. So that's for a high output. So now we need to find our power when we have a low output. And when we have a low output, as Ombalo had explained in the previous video, we saw that D3 conducts and T2 and T3. D3, I mean, sorry, I didn't label here, but D3 is this one here. My whiteboard is crashing, so I can't edit right now. But D3, this here, you see there are two diodes. So D3 is part of a multi-emitter. So D3 will conduct, the diode will conduct the CB1, and T2 and T3 will go into saturation. So when that happens, so our PDL is equal to VCC times ICCL. ICCL to mean subscript L for low, for it having a low output in the Ukumbuke. So when that happens, it means our ICL will be equal to what? It will be equal to, from the ICL from VCC, it will be equal to IB1 plus IC2 plus now the IC3, which will now include, which will go through the RC3, which we don't know about. Because pamoja hapo, it will be IB1 plus IC2 plus the IC3 that we don't know about. The IB1 going to RB1, the IC2 going to RC2, and the IC3, which will go to now the resistor value we're looking for. So that's where we are going to have an algebraic expression. Please, if you have a question, don't hesitate to ask. So our IB1 will be equal to VCC minus VB1 over RB1. So when we have a low output, our VB1 will not be the same as our VB1 when we had a high output, because these are very different conditions. In the condition where we had a high output, our T2 and T3 were in cutoff, but now they're in saturation. So our VB1 will be equal to the voltage across the diode, the CB junction. Let me stop calling it the diode 3, but the CB junction or VD3 plus, because T2 and T3 are going to saturation, VBE2 SAT plus VBE3 SAT. That's our VB1. So having said that, now it will be equal to 0.7 volts plus 0.75 plus 0.75, you get 2.2 volts. So our IB1 will be 5 minus 2.2 over 4K. You get 7 times 10 to the power negative 4 amperes. Now to find our IC2, this is VCC minus VC2 over RC2. Sawa. Okay. Then, but what is our VC2? Our VC2 is the VCE2 SAT across the T2 transistor plus the VBE3 SAT. I hope you can see that. Then our VC will be equal to, we know our SAT values, 0.2 plus 0.75, you get 0.95 volts. Our IC2 will now be 5 minus 0.95, this is the VC we just calculated, divided by the RC2 value, 1.6K, you get 2.53 milliamperes. So our IC3 will now be VCC minus VC3 over RC3. The IC3 is this one. This is where we want to put our resistor value. This is the resistor value we're looking for, yes? So VCC minus VC3 over RC3. Where are we now? Yes. And VC3 is equals to VCE3 SAT. Let me show you that. VC3, you see, remember when we said when we're having a low output here, we said T2 and T3 will be taken to, will go saturation, yes, or TTL. Sawa. So VC3 will be the same as VCE3 SAT. So that is going to be 0.2 volts. So 5 minus 0.2 divided by RC3 that becomes 4.8 divided by RC3. Remember, you don't know RC3. But in the question, we were given the power dissipation of 15 milliwatts. So we know power dissipation 15 milliwatts, and we know PDH, power dissipation when you have a high output, but we don't know PDL because now it's going to be in algebraic form because of this RC3. So having said that, PDL, we said our ICCL is IB1 plus IC2 plus IC3. So you do this, so our VCC is 5, PDL, now did I do here? Oh. So sorry, I've forgotten this step here. So PD is equals to PDL plus PDH, right? I was supposed to write that times 2 here. I mean times a half. So now it's 15 milliwatts times 2. PDL plus PDH is equals to 15 milliwatts times 2. Please, I've written this equation wrongly, but it's 15 milliwatts times 2. I forgot to put the half sign there. So PDL, what is this I did here? Yeah, I just forgot to put the half there. So PD is 30 milliwatts. No, what have I done? Wait. PD, this is the equation. This is how it is. PD is equals to a half PDL plus PDH. Sindio? Yes? So PDL plus PDH is equals to 15 milliwatts times 2. So PDL plus PDH is 30 milliwatts. I'll correct that and send the PDF. So just ignore that. So PDL, ignore this part here. This PD is equals PDL plus PDH is equals to 30 milliwatts. So PDL is equals to 30 milliwatts minus 5.125 milliwatts. 5.125 milliwatts is the PDH we found. Sawa. So PDL is equals to 24.875 milliwatts. Gosh, I hope I've not confused anyone with the power dissipation formula. I've just written it wrongly here, but PDL is 24.875 milliwatts. I was writing it in a hurry. So 24.87 that PDL is equal to 5 times the summation of this. When you make RC3 the subject of the formula, you find 2.75 kilo ohms. Gosh, okay. So now then there was the ECL. Okay, so now we're going to look at an ECL. Is there any question to do with TTL and finding the RC? Okay, so for the ECL, we usually do ECL. It's usually preferred because the transistors do not go into saturation, if I'm not wrong. So to find the reference voltage VREF, we'll say VREF. Okay, you've not read the question. For ECL gate, determine the following reference voltage, logic levels, VOH, and VOL, average power dissipation. And then you're told to assume that all transistors have VBE on of 0.7. So VREF is VB4. VREF here is, I hope you guys can see the VREF is equal to VB4 minus VBE4 on. Okay, so VB4, and what is VB4? VB4 is equal to VB4 is VB4. Oh yeah, and VB4, remember we are looking at this transistor Q4 here. the transistor Q4 here. So our VB4 is equals to, we found our VB4 is equals to VCC minus the voltage drop across R7. Sawa. Higher. So here we are going to apply a lot of voltage divider work and analog work. So remembering voltage bias, divider bias, how we did it. So we are going to say VCC minus the voltage drop across the diodes and the power supply, so that you can remain with the voltage drops across R7 and R8. Then to find that voltage drop at this junction here, you're going to say R7 over R7 plus 8 plus the voltage drop which remained. I hope I've not confused anyone. Okay, no one is saying anything. That means you guys are okay. So VR7, once you do the voltage divider bias there, you get VR7 is 0.58 volts. Then you subtract that from VCC and you get VB4. And your VB4 will be negative 0.59 volts. So your VREF will be VB4 minus VBE on. So it's negative 0.59 minus 0.7. Then you're asked to find the logic levels the output when it's high and when it's low. So when you assume Q2 is on, when you assume Q2 is on, what happens? When you assume Q2 is on and that Q1 and Q3 are off, are you guys seeing? Okay.
Yeah, we can see.
Okay, when you assume Q2 is on and Q1 and Q3 are off, you're going to say that VE2, we're looking for the output high and output low. So VE2 will be equal to VREF minus VBE2. So, and our VREF is negative 1.29. So when you subtract that, you find your VE2 to be negative 1.99 volts. So once you find that, you find your VE2. Now we go to our IE. I mean our I, the current through the IE3, the emitter current. So you're going to say VE2 minus, sorry, that's the wrong, the current through the Ebu, please come and explain this. I think I've confused myself somewhere. Gisheru.
Yeah, I'm here.
Ebu just, I've confused myself, but the
At what point?
Logic levels, Ebu go through that, but I think I've confused myself somewhere.
Okay. Then let me present it. Tell me when you can see it. Hopefully I won't get lost myself.
We can see.
Okay. There's this question. So for the logic levels, V output high and V output low. The reason as to why we're giving the assumption of assume Q2 is on and that Q1 and Q3 are off is so that we will eventually get V output high at V output high will be at 1 at V1 on the left, and V output low will be at V output 2 on the right. So if you go through the the working of sorry, I'm choking on food. I don't have COVID. Please. So if you go to the how ECL works, the notes are here. You'll go through them. So basically, ECL, the fundamental circuit of the ECL is a NOR gate. And if you add the extra output stage, you'll convert it to OR. And you know that OR gate and NOR gate are the inverse of each other. So when one is 0, the other one is 1. So by giving similar inputs, according to the truth table that A and B, you'll have V1 will go to high, I think, and VO2 will go to low, which is what we're looking for, V output high and V output low. So assuming that Q2 is on and Q1 and Q3 are off is assuming that A and B are at logic 0, which equates to minus 1.55 volts. You'll see that in the previous pages of this PDF. So that's why we made that assumption. So VE2 is equals to VREF minus VBE2, because we know that if VBE is equals to VB minus VE, then VE is going to be equal to VB minus VBE. And the VB in this case is VREF. So VE2 will be equal to minus 1.29, which we found above, minus 0.7, and you get minus 1.99 volts. So now to find IE3, the current IE, I think it's supposed to be IE2, because Q2 is on the top, Q1 and Q3 are off. So IE3 is equals to 0. So to find IE2, the emitter current through the transistor that's on, it will be VE2 minus VE over R3, which is just equal to VEE minus VE2 plus VEE. So therefore, IE2 will be equal to minus 1.99 plus 5.2 divided by 779 ohms. And you'll get an emitter current of 4.12 milliamps. And since Q1 and Q3 are off, IC1 and IC3, if we go back to the circuit, here's the circuit. Since Q1 and Q3 are off, IC1 and IC3 will be equal to 0. So IE2 for beta, I think, yeah, for beta is much greater than 1. IC2 will be equal to IE2. And also for, we're not entirely sure why this is, but we're assuming it's because of the whole thing of beta being much greater than 1. IC2 will be much greater than IB6, the base current for transistor Q6. So basically, all the currents that will be flowing through R2 will be Is that me? Let me check. Yeah, all the current flowing through R2 will be IC2. Therefore, to find the voltage VC2, we will do VCC minus IC2 or R2 times R2. VCC is 0, IC2 is 4.12, and R2 is 2.5 ohms. So 0 minus that will give us approximately minus 1 volts. And VC2 is equals to VB6 over here. You can see that, right? So if VC2 is equal to VB6, that means that if you go back to the circuit, VE6 will be equal to our V output 2. So we know that if VBE is equal to VB minus VE, then VE, as we found earlier, is VB minus VBE. So if we do minus 1.0 volts minus 0.7 volts, we get minus 1.7 volts. And as I stated earlier, in ECL, the logic 0 is equals to minus 1.55 volts. So minus 1.7 is even lower than minus 1.55 volts. So our V output low will be equal to minus 1.7 volts for this particular circuit. So now we need to solve for V output high, which is on this side. Since Q1 and Q3 are off, as the base emitter voltage will be below 0.7, that's why they'll be off. Again, you'll see that in the earlier pages. So have you guys been able to hear me this whole time, by the way? I hope I didn't.
We can hear you. We can hear you.
Oh, so if Q1 and Q3 are both off, that means that the voltage here, VC1 and VC3, will be equal to VCC, which is ground, which is the ground voltage over here. Since here, the ICs will be equal to 0, so there will be no voltage drop. So this will be equal to VCC. So to find VE5, you'll do this voltage minus this drop over here. So it will be 0 minus 0.7, and you'll get minus 0.7 volts. Therefore, 0 minus 0.7 equals minus 0.7. So our V output 1 is what will serve as our V output high. And V output high for this particular circuit will be minus 0.7 volts. Have we all followed up to that? Understood? Any questions? Anything?
Gisharu,
Yes.
hapo kwa VO2, you said VO2 is that what's VO2?
VO2.
The next page. Yes. Yes. You said VO2 is equals to VOL is equals to negative 1.7. You said if VO2 is usually negative 1.55.
Like the can I say default or standard?
Mm-hmm.
The standard value of output logic low in an ECL is minus 1.55. But with various analyses, you'll see that it's not always going to be equal to minus 1.55. It won't be fixed. It's not like written in stone that it's minus 1.55.
Okay.
They will range from different values because these devices are not perfect. Even for TTL, you'll find, see, you know that diagram for logic levels? I don't have it here. Right. Let me see if I can find it here. Is it? Yeah. So you know this diagram, this diagram here at the top, figure 3.4.
Yes.
Yeah. So like this is a good example of whatever logic level you have is not going to be fixed at one value. It will have a range. Okay, I don't even know if that was your question, but
Oh, my question was, what if you found your like the value? You said because 1.7 is greater than negative 1.55, we picked VOL as negative 1.7. So if we got, let's say, 1.2, will we pick 1.55?
It's a good question. Yeah. I think for that, I'll have to look for the logic levels diagram for an ECL before I can answer that question, because I don't want to lie. But if I had to answer you right now, I would still take the minus 1.2 as a logic low.
Okay.
I would still take it as a low in that case, but I'll look into it. We will look into it.
So thanks.
So, are there any other questions? Any other? I didn't see any other. Mike, you were confused about something. Do you mind explaining what you're confused about? It's 20 to 11. Okay. Or do we like move on? The ACL diagram on the right side. What about it? What parts? What part can I edit this thing? Okay. This thing doesn't work. Okay, never mind. Okay, never mind. What parts? What do you mean they ACL on the right side? Is it the part with the diodes? The line that has the diodes? Does the notion of cutoff and saturation carry here? No, Mike, Fiona started by saying that these transistors never go into saturation. They're always used in active mode, and that's why they're very good for switching. But they have very high power dissipation and poor noise margins. So saturation cutoff will not apply in ECL because they're always used in active mode. Could I go through getting VREF again? Okay, getting VREF was a bit confusing because we are usually used to VCC being at a positive voltage and VE being at ground or at minus something. So, okay, personally, how I looked at it was I assumed that VE was positive. Then I did my evaluation the way I usually do. The way you usually do for voltage divider. And then I just added the negative sign when I was done. And it worked. I don't know if it's like a one size fits all type of thing, but it worked for me. So if you subtract the drop if you subtract the drop due to these two diodes from 5.2, you'll get 3.8 volts. And we know that when we're doing voltage divider, you'll take the resistor that is closer to ground as a numerator. So that will be 907, right? It'll be 907 divided by the total resistance, taking out D1 and D2 because we've already solved for D1 and D2. We've already removed D1 and D2. So it will be plus 907 over 907 plus 4980. Then times the voltage that will drop, the total voltage that will drop across both resistors, which in this case is 3.8. So if you do that, you will get 0.58545999. You'll get this. You'll get this. This what you got. This one down here. You'll get this one down here. And then after that, I just added the negative. And then it ended up being minus that. And it was a bit of a shortcut, I won't lie. Because I wasn't understanding why we're taking R7. But yeah. But I think also what Fiona said was correct. Yeah, okay, that's my answer for that. Is that answer satisfactory? You're welcome. Are there any other questions? Okay, I guess not. Sasa, Fiona, unaweza, you can continue from there.
Yes.
Right.
Sorry guys, I saw the IE3 and it threw me off completely because I knew that the transistor 3 was I knew that the transistor 3 was off. I mean, Saskia, I'm confusing. So I gave the wrong alphabet, so it threw me off completely. I'm sorry about that. So Tuna had asked questions she had asked a question on question 3.3. It's on the DE book. So this question was quite tough for us. We were only able to, I don't want us to present it yet because we found IB3 to be 140 microamperes and it's asking for the short circuit current if the output Y is taken to ground. So we didn't understand how that, how when this short circuit Y thing is taken to ground, we didn't understand why the collector and the emitter are grounded at the same time. So I don't know if anyone has insights on that, please let us know and help us solve it because this guy has a tendency of bringing these questions. Also, she asked about the noise margin question. The voltage transfer characteristic of our logic gate is that in this diagram determine the noise margins. So this one we used this graph to get the noise margins. So as you can see, the dotted lines. And we know noise margin low for logic low, it's V IL minus VOL, and noise margin for a high output, we have VOH minus VIH. And that using this diagram, you can find VIH is there, where the slope just stops continuing, it starts now flattening out, and VOH is where the slope starts. VOL is where it's also where the slope starts to end, and which one haven't I said, and VIL is where the slope starts. So I think when you see the PDF, I'm going to send it once I change that current that I noted badly and the power dissipation formula. So when you apply this, we find our VIL to be 1 and our VOL to be 0.2. And then you find noise margin low, 0.8. Noise margin high, you have VOH minus VIH, so that's 4.9 minus 3.5. We assumed that the value here at between 3 and 4 is 3.5. So yes. Yeah, so we had a problem. The next question, also we need help. 3.4b, if two gates with the characteristics are cascaded, determine the overall noise margins. We assumed that okay, we also made our own kind of kinds of assumptions, but we only found VIH for the next cascaded, for the gate which is being cascaded, and we are not able to find this other. There are two parameters we are not able to find. So if you know how to get that one, please let us know, but we're able to do part A, which I've explained. So I think now we're just going to do a CMOS question. We had prepared so many questions. So obtain the function table of a circuit, and hence or otherwise determine the logic function of the circuit. So, so the function table is this. This is the truth table. When we have, okay, I have to go through this, all of it. When we have, as you can see, the C line, the input C controls, it basically controls the endmost part of the transmission gate 1 and the PMOS part of transmission gate 2. So, okay. Okay, Gisha will also please come and explain this one. Please. So yes, it's pretty easy. He has a shortcut way of finding it. I had to draw the whole truth table, but yes, I have to like do 0001, but I think he has a very nice shortcut of doing it.
Okay, so I'll take you through a question. I mean, you can see my screen. I'm presenting. Can you see my screen?
We can see it.
Yeah.
Okay, so this shortcut only applies to this question, to this circuit, because of how it is. But I'll use through the whole thing. I'll just walk through the whole thing. So, okay, for me, usually if I see such, I will. The first thing I'll determine is what's okay. Let me just check something. Is there anything on? So I think first of all, I need to show you what these weird triangle things depict. Right. No, it's in front. So yeah, if you have the class textbook, you can go to. If you have Mr. D's, Dr. Mwangi's, if you have Dr. Mwangi's textbook, you can go to page 94. So this is what so this is what is going on here. That's what we're looking at. So at the top, we have a PMOS. You have a PMOS, okay. Do you guys, you understand the workings of PMOS and NMOS in enhancement? Or do we need to like run through that? Please, someone say, just say, I can't see the chat.
Michael, do you need us to go through it?
Like how do we work? We don't have like anything written down, so.
I'm just saying go through it quickly.
Right, okay. So here's N-type enhancement MOSFET. So what happens then in the NMOS is that when it's in enhancement mode and the source and the substrate, these two will be connected to ground. Okay, leave that thing alone. It's connected to ground. So what happens in the NMOS and enhancement NMOS? N-type enhancement MOSFET, sorry, is that the source and the drain are highly doped with electrons N+ region. N+ region, and the substrate is P-type. And we have this SiO2 dielectric layer, and then this metal part, which is not the gate. Those are the parts of a transistor drain, gate, source. So in order to have a current flowing from the drain to the source, or vice versa, we'll need to form a channel here, over here, between these two places. We need to form a channel there. And the channel has to be of the same, with the same charge carriers as the drain and the source. So that current can flow. Like if we'll apply a positive voltage here, and then this is ground, so that current can flow in this general direction. In that direction. So the only way in which we can form an N layer over here, to form an N-type layer over here at the top, is if we push the positive charge carriers away. And how are we going to push them away? By supplying a high enough positive voltage over here. A high enough positive voltage over here will repel the P-type things over here. So with a sufficiently high positive voltage at the gate, we will form our N channel here. And then if you apply a positive voltage at the drain, you'll eventually get a current flowing through that way. Yeah, the drain. And this sufficiently high positive voltage is called V threshold. Is it somewhere down here? Okay. It's not. So yeah, this sufficiently high positive voltage is what we call V threshold, which will also be termed as VGS. In some parts, VGS and V threshold can be used interchangeably. So basically, that's how we get the NMOS to work. Are we good until there? We good. And PMOS is the opposite, because they are dualities of each other. Are there any questions? Any you can brush it. Okay, so. So P-type is it? Here's a P-type thing. You'll just do the same thing. I mean, you'll do the opposite of what I've just said. But you'll notice that in some questions, the substrate and the source will not be at ground. They'll be at a higher voltage. They'll be at some positive voltage. So that if you apply 0 at the gate, it will still form the channel. It will form a P-type channel in this case, over here. If you put the source and the substrate to be greater than 0 volts. Okay, I think that's quite explanatory. So where was I? I was here. so here's the PMOS here at the top. The PMOS is at the top, and you can see the substrate here is at VDD. It's higher than 0. It's at VDD, which means that if you apply 0 voltage at the gate over here, you're still going to form your P-type channel. And NMOS here is connected to ground, which means if you apply a positive voltage, say, yeah, 5. If you apply 5 over here, for example, you're going to get the NMOS to form that N channel and make it conduct. So, quick recap. NMOS need a positive voltage to make it conduct. PMOS, in this case, you'll need 0 to make it conduct because the substrate is at positive VDD. And this is the symbol. PMOS has a bubble at the top. Okay, so now, yeah, this is just the explanation of those terrifying triangles. Is that a question? Hold up, please repeat again. Transmission gate. Okay. So this is the structure of the transmission gate. We have a PMOS at the top and an NMOS here at the bottom. And the goal is to get what's here. The goal is to get what's here, what's there, to this side. Here's where we want it here. But in order to get this, in order to put this here like that, we either need this path or this path. But here, let me just put this up. Here, it says that here. I can't even highlight it, never mind. It says that the gate is always operated with complementary logic levels at the PMOS gate. So whenever there's a 0 here at PMOS, there's a 5 here at NMOS. And whenever there's a 0 here at NMOS, it's going to be a 5 here at PMOS. And if there's a 5 at PMOS, you won't be able to form the gate, the channel and to conduct. And if there's a 0 here at NMOS, you will not be able to form the N-type channel and won't be able to conduct. Is that good enough, Situne? Okay, so now to the question. Obtain the function table of the circuit in figure 2a, and hence others determine the logic function of this circuit. So for me, the first thing I check is whether or not whatever it is I'm working with is on or off. Because if the transmission gates are off, then they're not conducting anything, so it doesn't matter what's going into them. You're going to get 0 over here, 0 over here, or a disconnection, or it's just not going to flow this way. So what I looked at first was what is responsible for controlling the states of the transmission gates. And here, if you look at this line, for example, this line, this way and this way, we will see that it is C. C is solely responsible for the functioning of, we'll call this TG2. And if we come here also, here we see that once again, C is responsible for the functioning of TG1. So now let us do analysis for C. Let me take you, I will take you through the whole thing using what Fiona has done. So we have, here is our truth table. Here's a truth table 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So if we do 0, 0, 0, it means that first of all, we'll have a 0 at this PMOS over here. And we'll have, what's going on here? We'll have a 0. There was an, I'm sorry. I've confused you guys. Yeah, this one goes this way. This goes this way. And that way. And that way. I'm sorry. I hope no one is confused. It goes that way. And they will. Like this, through this inverter. And it goes up and it goes down. Yeah, I'm sorry. I hope no one is confused. So when you have 0, 0, 0, we have 0 here. The 0 will go through the inverter, become a 1. So we'll have 1 here, and a 1 here. We'll have 1 at the NMOS of TG1, and 1 at the PMOS of TG2. So from what I said earlier, if you have a 1 at the top, this TG2 is going to be off. It's going to be off. That will be off, and this one will be on. So for the case of 0, 0, 0, whatever output is being fed into TG2 does not matter because it's not going to conduct anyway. In this one, if we then do the analysis for the PMOS, you'll find that the 0 goes all the way up EV until here. And here we have a 1, which means that the NMOS is conducting and the PMOS is also conducting, which means that TG1 is going to conduct as well. So whatever is in A is going to go straight through here. If we have a 0, it's going to invert and become 1. Yeah, here's the first line. Hope that makes sense. And then 4, and you will notice that with this little analysis that you've done of the transmission gates, every time C is 0, TG2 will be off and TG1 will be on. Therefore, only the output of A is going to reach the inverter and it will be transmitted to the out. It will become Y. So if you look here at the truth table, every time C is 0, every time that C is 0, we will find that the output is the opposite of A. So for instance, in the first case, C is 0, A is 0, Y is 1. Here, in the third case, C is 0, A is 0, Y is 1. In the fifth case, C is 0, A is 1, so Y is 0. And in the seventh one, C is 0, A is 1, so Y will be 0. So. Now, let's do this one, this second one. We'll do this second one. So when C is 1, when here C is 1. So if we take this path right here, this will become 0. It will go up there 0. It will come down here 0. So we'll have a 0 at the PMOS of TG2 and a 1 at the NPMOS of TG1. And since these things work in complementary fashion, we'll have, we'll have a 0 down here, a 0 at the NMOS and a 1 at the PMOS, which will render TG1 off. And this will be rendered on because we'll have a 0 at the PMOS and a 1 at the NMOS, which will make them both conduct. So since this is off, we'll only take the path of B this way into the inverter, and then yeah. And if you look at the truth table, every time C is 1, Y is the opposite of B. Y is the inverse of B. Y is the inverse of B. Every time that C is 1, y is this B bar. Here we have 0, 1, here we have 1, 0, here we have 0, 1, and here we have 1, 0. So you can do all of these steps if you want. You can do all the steps for each variation of what it could be. You can do for all 8 for confirmation purposes, but yeah. So from what I've said, you'll see that this logic function operates like this. When C is 0, y is not A, and when C is 1, y is not B. Therefore, it's as if C is the decider of what goes through this circuit, right? It's like C is the traffic cop of this junction called transmission gate. So a little device that we know from 3.1 that works in this way is the multiplexer. You have multiple inputs and a single output, and you have a select line which chooses which input goes to the output. And again, since y is equals to not A and y is equals to not B, it's as if this thing works on active low basis. So therefore, this is the function table. This right here is the function table. And the function, the logical function that this circuit serves is, it's an active low 2x1 multiplexer. It's an active low 2x1 multiplexer with C as a select line. So yeah, basically that's it. Transmission gate questions are they're not difficult. And they're pretty straightforward. So I think
Ishiru,
yes.
there in your circuit diagram, don't you, like, wouldn't your output be equal to A if like C was 0, according to your circuit diagram, instead of being equal to the inversion of A?
If C is 0.
If like C was 0, y would equal A instead of equaling A bar.
Why?
Because I'm just looking at the circuit diagram, not the lower one on your bottom right.
This.
Oh, no, bottom right of the page.
This.
Yeah. Like, I understand how you've gotten to that when C equals 0, y should equal A bar. But now I'm wondering, according to that second diagram you've drawn down there, doesn't that mean that when C is 0, y will equal to A and not A bar, like you've shown earlier?
True. I think you put like a bubble over here. Put like a bubble over there and like a bubble over here. Or something. I don't know. I think the multiplexers have control switches. I'm not sure.
Yeah.
We're in a bit of a hurry. So I think putting bubbles over here should suffice.
Okay. Thanks.
Yeah. So. That's how. You think the bubbles?
Cameron's. There's some questions.
Active low. Active low. Active low. Active low. Active low is when something is enabled with an input of 0. I think. You think? I'm saying it's active low. Wait, there's so many questions in this question. Situn asks, does this apply to other gates when C is 0, y is equal to? No, it does not apply. This is just specific to this circuit. Other circuits will have different behaviors. It just so happens, and in this circuit, this happens, but it's not a standard. Kamara and Elizabeth both ask on active low. So no, active low, how do you explain active low? You know how when we're let me just use this as an example. When we had a control switch, we had a bubble here, and then we had a control switch here. Okay. Be like a switch thing. So I'm so sorry. This thing is so fake. I'm so sorry. That, and then we have one line that would go to ground, and then another one that would go to whatever VCC is. Whatever VCC is. Then there would be a switch thing. So you remember how, like, when you have this bubble, it means that when this control switch is connected to ground, it means that that's when the chip is enabled. Like, it works in reverse. Like, the internal circuitry is a wire, and then there's an inverter. There's an inverter thing in there. So when you connect this thing, when you connect that control switch to ground, whatever is there will be inverted through here, and you'll end up with a 1 going into it, and that one will activate or inhibit that thing, the specific chip or gate that you're working with. So that's what active low means. I guess you can think of it as it's activated by a low input. That's how you can, that's like a good way to remember. So what I think, why I think this menu was called active low is because I think actually I'm not very sure if I will give me a few minutes. Meanwhile, we can move on to the next question. I will try and figure something out. Okay, Alvin is coming to my rescue, so everyone listen to Alvin. And the time is 11:15. I don't know if you guys would like us to continue. I'm sorry this thing has taken so long. Fiona, okay, it depends on what people want. You to end the line. What's left? Let me see what's left. These are 2 questions. This is quite a lot. Do you guys really want us to continue?
Would
you allow us to continue?
We can tackle the one on the CMOS, because it's just CMOS that we've not covered. We've covered CMOS as a transmission gate. If not, you could go ahead and do the one for when you're given a Boolean expression and how to convert it to a CMOS circuit.
Would you want to take us? Fiona.
Yes.
Fiona.
Yes.
Do you want to take us through?
Okay. Okay, so.
Sounds out.
Okay, so mostly questions are, when you're given a PMOS question, it's basically to describe how it works. And I think Gijiro has covered part of that, and Nigel also covered part of that. But I've also seen something we forgot to tell you. Mostly in the textbook, we cover TTL NAND gate, but this is a TTL NOR gate. It looks like this. We've shown you, we've calculated it for you and shown you how it is, so we won't go through it. So yeah, this is a calculation for TTL NOR gate. It's not in the textbook. For ECL, what is remaining, it's when you're asked to, you'll be asked to draw a 3-input ECL OR gate. I have been trying to look for it, but I've not found it. If someone finds that, please send code group. So when you're given a Boolean expression and you convert it to CMOS, so you have y is equal to that. So we know that the CMOS, it inverts eventually. So step 1 is to do the inversion of all of it. Then step 2 is to construct using the NMOS logic so that you can know how it's going to look. So we all know how NMOS, it's like, yes, so NMOS is like this. Then step 3 is to construct the expression using PMOS. So once you know that, and we know our A is prime, it's not A, it's A prime, so you'll have to use the CMOS inverter. And just put this here, but eventually you'll use a CMOS inverter for your A input. Then, because it's A and B, in your NMOS, A and B, it's going to be in series, plus B and C. So B and C. I hope you can see that. So that's A and B, or B and C. That will go to that. This will go to this. I hope you can see that. Then you and we know NMOS is a duality of PMOS. So when you construct the PMOS, if A and B was in series, now it will be in parallel, and B and C were also in series. So we see here they become parallel like this. So whatever was series becomes parallel, and whatever was parallel becomes series. I think duality is pretty much easy. So we know NMOS is always down. It's the one which is always down. So step 3 now include the CMOS inverter for A. And once you include the CMOS inverter for A and include output Y, remember you see here our output Y. Our output Y is a bar Y, same as here down. You'll see our output Y is a bar Y. So yes, so the final thing, it now becomes this. I hope you can all see. So so this is the inverter here for A. This inverts A and it becomes a not A. And then this is where our Y bar becomes Y. Sawa. So, and we note that this part up here is the PMOS. And this part down here is it's the NMOS. Then when you combine both of them, you get the CMOS. Sawa. Okay. Yeah, and then down here you'll have the truth table. For that, I don't think there's any point for me to go through that because of time. So I also, but it's that if you have a question on how we got to the truth table, please don't hesitate to ask. Why are negative DC voltage? Why are negative? I mean, why is it that we are usually for ECL usually have VEE, a negative VEE, and we never have a positive VCC? yani it's grounded. And the reason, it's because the ECL is operated with negative power supplies to protect the output transistors from any unintended short circuit to ground. I hope that is clear. And yes, and I wanted you to note that this CCL question in the exam is the same as the one in the book. The only notable difference is that here he's just separated this part and just done this to ground. It's pretty much the same thing, and yes, it's just, and the VREF has now been changed, and Gisheru took you through how VREF, we find VREF. This has been changed, just change values been changed. Which other question? So what is a transmission gate? I think Gisheru has answered that. A logic control switch that is often used in the realization of logic modules. So a transmission gate, we saw that it worked as a 2x1 multiplexer from our example. And he also explained the principles on how the operation of a MOS transmission gate. And then he further goes on and asks a 2x1 how to implement that. So we are seeing this question is repeating very much. In what ways are CMOS logic devices considered superior to both NMOS and PMOS counterparts? And that's because CMOS, I think it has a low static power dissipation because of the arrangement. So because PMOS and NMOS cannot be on at the same time, so therefore there's negligible current. It's very small current which is drawn. And then they further go ahead and ask you to show how a 2-input NOR gate for CMOS is implemented, and it's here. I won't go into it very much. And then because you've been shown how a CMOS works, then what makes the ECL family faster than both TTL and MOS families? So ECL, it's faster because it does not, we say that it does not go into saturation. I think, let me see, yes. So because of that, it's much faster. I hope I've not forgotten anything there. Then this was a question I was saying, I don't know, this one, give a circuit of a 3-input ECL gate to implement an on function. Hapa ndio pia tujajibu bado. So unaweza tusaidia na hii pia. So yes, I think that's it. Pretty much everything is just redundant here. The questions we've done, it's just with different conditions. I don't think there's anything to cram because everything is in the book. So yes, if I've forgotten to add anything, yes. Okay, I think I'm done.
Okay, thanks, Fiona and Gisheru. I'm seeing it's 11:30. Although I don't know when you can present. Vin. Oh yeah, there's also math. So how do you want to conduct math on Saturday?
Can you go through the working centers?